Hi everyone, welcome to Sensor Fusion with the Sony Spresense and CommonSense. I'm David Tischler, a developer program manager at Edge Impulse. In today's webinar, we're going to cover who is Edge Impulse. We'll talk about the Sony Spresense and the CommonSense add-on hardware, talk about what is Sensor Fusion. We'll build a Sensor Fusion model using the Edge Impulse platform and then deploy that model onto the Spresense. And we'll do that from a frame of reference of imagining we'd like to build a smart running jacket. The jacket should have two product requirements. It should be able to determine if we're running or just differentiate from normal activity. And it should have a series of LEDs or lighting that turn on at night for safety reasons. To prototype this concept, we can use the Spresense, CommonSense add-on board, and the Edge Impulse platform. And then moving from prototype to production is easy when the time comes. Let's get started. First, let's look at Edge Impulse. Edge Impulse is the leading development platform for machine learning on edge devices. It allows you to build a machine learning project in 4 easy steps. Collect your data, design an algorithm, test the built model, and then deploy the model to an edge device. In the context of our Smart Jacket project, what that means is collecting motion and light intensity from the CommonSense board, building a model to recognize those motions and lighting conditions, testing the model's performance, and then deploying it to the Spresense. Diving deeper into each stage, collecting data can consist of gathering data directly from a sensor in the field or connecting to external locations like an S3 bucket or a Google Cloud location that has an existing data set. And the Edge Impulse Studio has tooling in place to inspect data elements and curate your data set. Designing an algorithm is easy. It's intuitive with the use of learning blocks and processing blocks. And the default settings that are pre-populated will work for most projects. You can also customize and edit any of this if you're a more advanced user. Testing is simple with the ability to classify test data that was set aside during dataset collection, or use your built model to classify live data coming from a device. Finally comes deployment, and while we're going to use the Sony Spresense today, other hardware targets do exist, or you can always export to C++ or WebAssembly and use your model on nearly any device. As I mentioned earlier, our hypothetical smart jacket needs to be able to differentiate from 4 distinct scenarios: running in the daylight, running in the dark, other activity in the daylight, or other activity in the dark. There's probably a case that could be made for walking in the dark, but there's some wiggle room there, as you might be on a city street, you might be in a line, you might be with a group of people that find it a bit odd that your jacket is lighting up. So we're going to leave that one out for now. But in the case of running motion and dark, that's when we'd like to activate our built-in lighting. Next, let's take a look at the Spresense and the CommonSense in detail. What I have on my desk here, and what we're going to be showing off today, is the Sony Spresense. And on top of it, I have added the CommonSense add-on board that adds an array of sensors. Starting with the Spresense, as you can see here, it contains a Sony CXD5602 processor, which contains 6 ARM Cortex-M4F cores. Plenty of I/O with GPIO, SPI, I2C, and more, especially when the Sony expansion board is used, but it's not required. It also has 1.5 megs of memory and 8 megs of flash, a camera connector, and at 50 by 20 millimeters, it's quite small. And then plugged into the top of the Spresense, I have the CommonSense board, which is designed and manufactured by SensiEDGE. And this is a nice add-on for machine learning projects because it has 10 sensors on board: air quality, accelerometer, magnetometer, gyroscope, temperature, humidity, pressure, microphone and proximity, and a light sensor. Here's a fully assembled unit with a camera as well, though we don't really need a camera for our smart jacket use case. Checking in on our agenda, let's see how we're doing. So far, we've covered Edge Impulse and the Sony Spresense and CommonSense. So next, let's talk about sensor fusion. Let's define sensor fusion. It's actually no different than what you may already be thinking. It's the process of combining data from more than one type of sensor or sensors in multiple locations to build a better machine learning model. In the case of the CommonSense board, we can combine data from any of the 10 sensors. And as I mentioned earlier, for our smart jacket idea, we'll use the accelerometer and light sensors on the board. It's easy to choose your sensor combination directly in the Edge Impulse Studio, which we'll get started with right now. To begin, you'll need to go to studio.edgeimpulse.com and create a project. If you don't already have an account, you can go ahead and create one. When you begin the project, you'll see an option for choosing between developer or enterprise. Developer is a free account. Enterprise is a paid plan, but there's a 14-day free trial to get you going with. You'll come to the dashboard, and the first thing we'll need to do is collect our data. As I talked about earlier, several options exist for getting your data into Edge Impulse. You can upload existing files directly in the studio. You can capture new data from within the studio. You can upload via CLI, connect to external cloud locations like an Amazon S3 bucket or Google Cloud Storage. For this webinar, though, we're going to capture data directly from the CommonSense board. You'll need to connect the Spresense plus CommonSense to Edge Impulse, and that's done via a little bit of CLI tooling that gets installed. I'm going to use Linux, but Mac and Windows versions exist as well, and there's a flashing utility that's included. We'll then use that to flash the firmware onto the Spresense and then run the Edge Impulse daemon, which will attach the Spresense to the studio. You'll notice when you click on devices from within Edge Impulse, there's none there yet, but after you run that daemon, then the Spresense will show up in your devices list. Once it's there, we can begin to collect data. Now, for this webinar, I originally intended to place the Spresense into an armband, attach it to my arm, and go out for a run in order to collect my data set. But it turns out I couldn't quite get the film and footage that I really wanted and then show you how to bring that data in. So I simulated a running motion. I noticed that when I had it in the armband, I had about 3 to 4 inches of movement in a almost pendulum style motion. I then simulated that simply by moving the board on my desk in order to collect my data set. It's not perfect, but for demonstration purposes, it'll do the job. I also collected data of the board just sitting idle, and I did both of these in both daylight and dark conditions. Once I've got enough data, in this case I collected, you can see there, 18 minutes across all of the data set. You could probably do a bit less. More data builds a more robust model, but this was enough for me to get a reliable model, which I'll show you in a few minutes. But it's pretty easy. You just choose the inertial and light sensor and click the start sampling button there. And then once you've got your data set collected, we can move on to impulse design. Building an impulse consists of 3 main blocks: an input block, a processing block, and a learning block. And this is the beginning of the machine learning pipeline here. There's default recommendations that'll be provided that'll work for most use cases. You can also customize this if you need to. All of this is documented over in our docs, which I'll take this link and put it into the video description for you. The next step in the impulse design is the feature generation. And this is a spectral features block, and you can see the DSP results that came for each individual data item that was collected. I'm going to click on Save Parameters, and we'll move on to feature generation. And we can see already that the features separate out into clusters pretty nicely. So this is encouraging here. we can see that there are clusters of data and DSP results in the idle daylight, idle nighttime, other daylight, so on and so forth. From there, we're going to move forward to the network classifier, neural network classifier, and begin the model training. Again, there's a lot of options, there's a lot of settings, but it is all documented. And when you're ready, you can click the Start Training button. The training output will show you, it's over on the right-hand side there, as the model is being built. And once it's complete, you'll see, using a validation data set, what sort of accuracy and clustering you achieve. And again, I came away with 100% accuracy. I'd say that's probably because my data is separating well, and each of these motions are fairly unique. And we can see there again the clustering of the data, of the model classification. The last thing we'll want to do before deploying it onto the board is do some testing. During the data collection process, some of the samples are set aside. Those unseen data points are not included in the creation of the model. You can then use that unseen data to test with. You can also connect to the Spresense and take live samples from the Spresense and run that sample through the algorithm that was created to see how it's classified. And we can see here the classification result of one of those samples. And again, you can see the spectral features are clustered out very nicely. So with that said, we've got our model built. The next thing we'll do is deploy it onto the Spresense. Now that our model is built, we need to package it up and get it onto our board. We'll need to build firmware, flash it to the Spresense, and then give it a try in the real world. If everything works well, we can continue on our path from prototype to the physical construction of our hypothetical smart jacket. First, we click on deployment, and we get quite a few options here. I'm going to select the Spresense plus CommonSense binary and build a single download that has the ability to run inference and display results via CLI output. However, you can also choose to build an Arduino library, C++, or WebAssembly, and those options are probably a bit more flexible because you can then integrate the library or the raw code into your application. Generally speaking, your machine learning capability is part of a larger system, like in the predictive maintenance world where you want to monitor equipment and the inference results need to be transmitted back to a central operations center for monitoring or integrated into alerting or notification systems. But for our demonstration purposes, this binary will work great. So we can scroll down to the bottom of the page and you can click on Build Model. It'll take a few minutes to run through the process, but at the end, a download is generated and we just need to unzip it. Then, with the Spresense connected through USB, you run the flash command that was included in the zip file. Like I said earlier, there's Mac, Linux, or Windows. It'll push the firmware to the board, and then we can run Edge Impulse Run Impulse, which was included in that CLI installation, to start inferencing. You can see here some of my results already being captured from the Spresense. Now that we've walked through the entire process from data collection to model creation to flashing the firmware here in slides, let's drop out and do a live demo. Give it a try. Okay, we're in the Edge Impulse Studio here. I'm on the dashboard, and on the left I can click on Devices. I can see that I have a CommonSense that's been recognized. It's got a little green dot here representing it, that it's currently connected. And you can see it's got the USB connection hooked up at the moment. On the left, I'll click on Data Acquisition. And this is where all of the data that I collected during my curation process is housed. I can click on any of the samples that we collected, and you'll get a feel for the sensor values over the course of 10-second intervals that I recorded the data in. This one here is running at night, and you can see a nice pattern of activity along the Z-axis of the gyroscope as I was simulating running motion. There is some activity on the X and Y axis as well, but we don't see any red, green, blue, or infrared because I had the light sensor blocked out. Let's come up here to do a filter, and we'll take a look at the opposite scenario, idle, daylight, grab a sample, and we can see that there's no motion, there's no accelerometer or gyroscope data, but there is red, green, blue, and infrared. Let's take other daylight and see what that looks like. So here we've got some random motion, random activity, and as the Spresense was moving around, the light intensity changed as well. And then finally, let's go over to running in daylight. And we'll see, again, that nice pattern on the Z-axis of the gyroscope, some movement along the X and Y axis, and a bit of change in the light intensity. But the fact that it's there at all, red, green, blue, and infrared, represents that we were doing activity in the daytime. On the left, click on Impulse Design, and we can see that our learning and processing blocks are already configured and set up. We're going to do spectral analysis on all of our sensor inputs, and spectral features are going to be analyzed like I showed you in the slides earlier. Here are those DSP results from the sensor. Again, we can see that nice, almost like a sine wave representing the running motion, but you can choose any of the data points that were collected. Here's another one. Again, looks pretty similar. And then finally is the classifier on the left, like I also showed, where you can go through and fine-tune the model creation. And you'll see the output, because this one's already been run, of the model. And there we can see that clustering. And we'll see this more in detail in just a moment when we put the model onto the board. Okay, so I've got our Spresense plus CommonSense back on my desk. And let's go ahead and start the inferencing on the board. Over in the command line, I'm going to run edge impulse run impulse, like I mentioned earlier. And this is in a VM, so it takes a moment to get through the USB pass-through. But once it finds the device, we'll go ahead and see inferencing begin. It's in 2-second intervals. And the Spresense is sitting idle, and it's pretty bright in here. So we can see, sure enough, we're inferencing as idle daylight. Let's go ahead and make that a little larger. There, we can see that better now. If I just grab the board and move it around a bit, we'll get other daylight. It knows that it's moving, but it's not the running motion. The running motion I used, like I talked about earlier, when I had it on my arm, I noticed it was about a 3 to 4 inch pendulum swing. And there we can see running daylight is being predicted. This is how I trained the board, and sure enough, it can recognize that motion. Now, this might get a little tricky to simulate nighttime in here. It's pretty bright in this room. But if I put this little post-it note over the light sensor, we get idle night. And if I move it just a bit, we should get other night. Yep. Now let's bring this back around. This will be the most difficult one of all to simulate. Let's see if I can get it running at night. So there we go. We've got all 6 of our classifications being predicted fairly accurately. Let's go ahead and take a quick pause here, and I'll get this disconnected. So we were able to demo the 6 different unique scenarios successfully, which is pretty neat. If we think about this from that prototype to production perspective that I've been talking about, we need to consider the hardware and the firmware and an application and fabrication of the actual jacket. The firmware, like we just talked about, is easy to build using the Studio. And I showed you the direct binary for testing purposes, but like I mentioned, the more robust solution is to download a library or raw C++. You can modify that base firmware that we used, though. It is open source on GitHub. The hardware can get pretty interesting. We used a Spresense and a CommonSense, which is easy to prototype with, but at production scale, with millions of units being produced, you probably want to build a slimmed down custom PCB around the CXD 5602 that has just enough I/O or pins to toggle the LEDs. And that toggling of the pins would be handled by your application. It'll need to listen for the inference results coming from the model and then control the lighting by toggling the pin high or low based on those results. Of course, the physical production of the jacket. Now, I'm not a garment expert, but I have to believe a small PCB could be sewn directly into a pocket or pouch in the sleeve on the upper arm, and then cabling the lights could be run along the seams to the LEDs that are sewn directly into the front and the back areas of the jacket. So there you have it. A hypothetical, but completely possible smart running jacket built with the Sony Spresense. Let's go ahead and take questions, or if you're watching this on demand and have questions, just pop them into our forum and we'll get them answered. Thanks.